Hi guys, today's video is going to cover graphing exponential functions and also going to cover the exponential equation and how to decipher that. First of all, though, we're going to back up and we're going to look at linear equations because that's something that we know how to use, and we're going to kind of use that as a comparison point. So for instance, we know that y equals mx plus b is our slope-intercept form, and when we graph that, it creates a straight line. And we also know that the m stands for the rate of change. That gives us the slope of the line. And the b is the y-intercept, or the starting amount. So when we're looking at word problems, for instance, we look for, how much did you start with, and then how much did you add to it every time. That would be y equals mx plus b. And then our graph, we're looking at where is the y-intercept and how much is it going up every time. So we know what linear growth looks like. That's you're adding to something, it's growing. And we know what linear decay looks like. It's going down. Also, we know that linear decay has a negative sign in front of it. That the negative slope is what makes that line go down. And so that all is review to us. Let's think about right now a couple of examples of when would you talk about linear growth or when would you talk about linear decay. So I'm talking about like real world examples. Can you stop for a minute right here and see if you can think of any real world examples? Okay, hopefully you came up with at least one example in the growth category and at least one example in the decay category. But some examples that I came up with, yours will probably be different. But an example of growth, if you put money in your piggy bank every week. So you're not putting it in the bank on the, in an actual bank, you're just putting it in your piggy bank and you're putting in $5 a week or something like that. Okay, I then have the price of a bag of candy, and that probably needs to be explained a little bit. Like, when you go to those stores where it's like in a barrel and you scoop out how much candy you're going to have. Well, it's priced per ounce. And so if you have 5 ounces, it's a certain amount of money. You add another ounce, it goes up more. You add another ounce, it goes up more. So something like that, where the price of the bag depends on how many ounces you have put into it. Okay, those are some examples. Hopefully you have some other examples as well. Example of linear decay. So let's say you owe your parents some money. They loaned you some money for something and you're having to pay them back. Okay, so if you're paying them off $20 a week, then that would be linear growth. Linear decay. You're just paying them off a set amount every week. And so on your graph, it goes down $20, down $20, down $20, down $20, etc. Or let's say you're going to lose weight. You need to participate in a sport, whatever, and your coach says you need to lose whatever. So you're going to lose some weight. If you are losing 1 pound per week, then again, your graph of your weight would look something like this, going down 1, down 1, down 1, down 1. Now, something to think about is how sustainable is it to lose 1 pound per week? Or maybe going back to paying off your debt to your parents. Are you ever going to get to zero? Well, yes, your parents are going to get all of their money back. You're going to owe them $0 at some point. All right, let's think about, can you lose 1 pound a week? Well, no, because eventually you're going to reach a point where your body cannot lose any more weight. So hopefully you stopped dieting before that happens, because we don't want you at 0 pounds. But those are some examples, and some things to think about is how much is it going down? It's going down the same amount every week or every month or what have you. It's going down the same amount. Okay, some differences then, because then we get into exponential. And exponential growth is a little bit different. So first of all, take a minute to graph these. Notice that it's starting out, this is not exactly flat. It might kind of look flat here. It's not supposed to be totally flat. It's supposed to be just like going up a little bit, but then it goes up a little bit more and a little bit more, and pretty soon it's going up a lot. That is exponential growth. All right, exponential decay. We have a lot of something and it is decreasing, 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 decreasing. So that's an example of that. Once again, I want you to pause the video here. Think about, can you come up with at least one example of exponential growth and at least one example of exponential decay? So once again, I'm sure we have different examples, and that's great. Some examples that I happen to stick with money on both of them, but I have you're putting money in a bank with interest. Okay, if that is gaining interest, that is exponential. Anything that has some kind of a rate with it, if it has a rate or a percent that goes with it, then that is going to be exponential. Same thing, credit card debt. If you owe money on a credit card, even if you don't buy anything more, you will have exponential growth in your debt because there's a percent rate. They don't charge you a set amount, they just charge you a percent, and it's going to increase. Other examples you might have thought about is a lot of you are taking biology right now. So if you have some kind of cell division, some kind of bacterial growth, things like that, those will be exponential as well because they're growing at a percent rate. Okay. Exponential decay. Once again, the decay has to, because it is that word exponential, it has to have a percent decrease. And so the population is decreasing by 5% each year. Maybe you have a population of turtles or you have a population of whatever. If it is decreasing by a certain percent, that is exponential decay. The activity we did the other day with M&Ms, and you are approximately losing 50% of your M&Ms every time. So that would be exponential decay. Another example of this would be going back to biology, or maybe this would be chemistry, but if you are taking a drug, well, when the drug leaves your body, have you heard of half-life? All right, if something has a half-life, that means it's getting cut in half over time, and that's how drugs typically work. They typically have a half-life. Same thing with radioactive material. It has a half-life. And going back to what I was talking about before up above, like, is your weight ever going to get to zero? Well, with exponential decay, it typically will not get to zero. It will get lower and lower and lower and lower and lower, but it won't ever get to zero. And so an example of that with, let's talk about the radioactive activity. If you have a radioactive material, it has a half-life. And so maybe it has a half-life of 100 years. I don't know. So after 100 years, you will have half of that material left. And then 100 years later, you have half of that. And 100 years later, half of that, and so forth. But you're always having a half of it. So it's never going to get to zero. It's going to just decrease more and more every year. All right, those are examples of exponential growth and exponential decay. And so now let's go ahead and start talking about what are the equations that we use for these. So let's turn the page. This page we're not going to talk about in this video. We're going to do it in class tomorrow. So let's go ahead and turn the page again. And so here we have the general model for an exponential function is y equals ab to the x power. And just like we understand y equals mx plus b, and we know what the m does, and we know what the b does, and we know where the y-intercept is, and so forth, this equation also, if we know how to read it, we will know some similar information. And so one thing is, your a is your initial amount, and then we can also say that that is going to be the y-intercept. And b is the growth or decay factor. And so we'll get into some examples of what that means a little bit. So right now, just realize that that tells you if it is going to be growing or decaying. And what we have is, if that number, that b, the number that is being taken to a power, and maybe another thing to remember, order of operations says that we do exponents before we multiply. So in other words, I don't know if you want to put in a little dot here to remember that it is only b is the only thing being taken to the power. The a is not getting taken to that power because we do exponents before we multiply. And so that b is what's getting taken to the power, not the a. And so if that b, the number that is getting taken to the power, if that is greater than 1, when we take it to a power, it is going to get bigger and bigger and bigger. All right, so for instance, let's just remember, like 2 squared, well, that's 4. 2 to the third, that's 8. It's getting bigger and bigger every time. But what if that number is under 1, between 0 and 1, for instance? Well, what is 1/2 to the second power? 1/2 to the second power is 1/4, and 1/2 to the third is 1/8, and so forth. So it's getting smaller and smaller and smaller. So if the number that is being taken to a power is between 0 and 1, it will be decaying, whereas if that number is greater than 1, it will be growing. And so over here on the margin, I have some things, and some of this is just a repeat of the information over here on the right. But on the left, I have it in the margin. That A, interestingly, is our y-intercept. When we look at these in Desmos, and we'll do that tomorrow, you'll see that whatever that number is in front, that's going to be your y-intercept. The B is whether it's growing or decaying. And if it's greater than 1, it's growth. If it's less than 1, it's decay. But that also kind of gives us the slope of the curve. So I'm just going to draw an example. And you don't need to draw this in yours, but just so you can see what I'm talking about. All right, we might have an exponential growth that looks something like this. It takes a while to get started, and then once it gets started, it's going pretty good. But we could also have an exponential growth problem that has the same y-intercept, but it goes up much faster. And that is determined by that B. That if this, like this green one here, this might be like, the B might be 5, whereas this one, the B might be more like 1.5. So the higher the number is, the kind of the steeper it's going to be. Okay, in this next section, I want you to look at these 6 examples here and decide whether they are exponential growth or exponential decay. So pause the video, see if you can figure out which one's which, and then we'll come back and go over them. All right, so as you went through here, A, B, and C were all decay because the number that is getting taken to a power is less than 1. Now, the one you might have a question about is example C, and so we'll talk about that here in just a second. And then over on D, E, and F, these are all growth. 3, that's bigger than 1. 17/10, that's bigger than 1. And 1.63 is bigger than 1. So anything bigger than 1 being taken to a power is growth. All right, let's go back and talk about C. That was the one that we hadn't talked about before. So why is 2 to the negative x considered decay? Well, remember a negative number, or excuse me, a negative power is actually like 1 over. So we could rewrite this as y equals 1/2 to the x power, because negative x means 1 over, so that's 1 over 2 to the x power. So that's why that one is decay, and that's the one that people kind of get tripped up on sometimes. All right, so this equation, y equals a times b to the x. That b, in this equation, this is another form of the equation, but we just changed it from b. Instead of calling it b, we're calling it 1 plus r to the t. And then this is a little bit more specific, and we'll talk about why is it 1 plus whatever. This would be when you have a percent increase or a percent decrease. And so if it is 1 plus r, that's a percent increase. If it's 1 minus r, that's a percent decrease. And so A, once again, that's the same A. It's your starting amount. That's your y-intercept, or like if it's money, it's how much money you started with. And then R is the rate, is the percent as a decimal, and T is the time. So for instance, let's do an example. Let's say that the rate is 25%. If the rate is 25% and it's increasing by 25%, then your B essentially is your 1 plus R is your 1.25. But if it is decreasing by 0.25%, then that's going to result in a 0.75 to the t power. And so if it's a 25% increase, it's 1.25. It's a 25% decrease, it is 0.75. All right, let's look at some examples. And there's just all we're going to do with these is we're going to start off by setting up an equation, and then we will go ahead and put it into our calculator. So in the year 2000, there were 281 million people in the United States. Suppose the population is increasing 1.24% annually. Write an exponential function to model this situation. All right, let's talk about what is 1.24% as a decimal, because we don't want to include the percent in there. We want to change it to a decimal. And so if we change that to a decimal, isn't it 0.0124. That's what we're talking about. So if we set up our y equals 1 plus r to the t, so I'm using this equation, y equals 1 plus r to the t, then we're going to have y equals, A is the starting amount, 281 million. Now, I'm not going to write all my zeros. I'm just going to remember that that is million. And so we'll deal with that in just a minute. And then we're going to have 1 plus 0.0124 to the t power. So that is our equation. So that's write an exponential function. We did that. Next part, use your function to approximate the population in the year 2010. So now we are going to use that same equation. And what do you think my exponent should be here? We started in the year 2000. We're now up to the year 2010. So let's call that a power of 10. And so now you're just able to plug that into your calculator. Do that. Plug that into your calculator and see what you get. All right, you should get 317.85. All right, let's think about that number, 317.85. What is missing from this? Well, this is actually in millions. Remember a second ago I said I just wrote 281, but it's actually 281 million. So this is 317 million people. So it's 317.85 million people in the year 2010. Okay, so that's how to set it up with the equation. And then all you have to do is plug that into your calculator. All right, let's look at another example. The population of a certain animal species is decreasing at a rate of 3.5% per year. You have counted 80 animals in the habitat you are studying. Write an exponential function to model this situation. Pause it here and see what you can come up with. Okay, so you should have come up with y equals 80, that's your starting amount, times 1 minus, because we're decreasing, 0.035, because that's a percent, we move it over 2 decimal places to the t power. Or if you put that 1 minus 0.035, you would get 0.965. And so now it says use your function to approximate the population in 5 years. If you haven't put that into your calculator yet, do that now. Okay, if you put that into your calculator and you put in the exponent of 5, because that's our time, 5 years, put in it for t, and we should get 66.9. All right, and then there's a question of, well, should that be 67? Should it be 66? You know, that is definitely a good question. And this is a certain animal species. Probably it's not going to be an exact number. So we can say 67 animals. If you said 66 animals, that would be fine. In reality, it might be 65. It might be 68 because it's nature. It's not going to necessarily follow a specific mathematical formula after just 5 years. Now, over centuries, we could do some estimation, etc. All right, last question. Cellular phone usage grew about 26% each year from 1995 to 1999. In 95, there were about 34 million users. How many were there in 1999? Once again, let's pause the video here, see what you can come up with. All right, your equation should be y equals 34 times 1.26 to the t, or you could just call it 34 times 1.26 to the t. Either one, I don't care which one you have. And then if we go ahead and use our equation to approximate the number of users in 1999, well, what's your power going to be? Because it's not going to be 99. Basically, how many years later is that? Well, that's 4 years later. So we're going to put in a 4 there. So go ahead and plug that into your calculator and see what you get on your calculator. And so when you plug it in, you're going to get 85.7 million users. And in this case, we can keep that decimal because we're talking about millions of users. So that 0.7, we're not going to round that or anything. We'll just leave it as it is. All right, those are the basics that you need to know on using the exponential equation and how to do some exponential graphs. We will continue to work on this in class tomorrow.